this video, we're going to continue talking about ordering and comparing numbers by looking at examples 5.3 and 5.4. Example 5.3 says, which number is smaller, negative 2.1 or negative 2.7? Write the answer in mathematical notation. So here we have two negative numbers, so we can't use our convenient fact about negative and positive numbers. So we're just going to use a number line. What I'm going to do is draw out the number line from 0 down to negative 4, or from negative 4 up to 0. So this is 0, this is negative 1, this is negative 2, negative 3, negative 4. I'm going to mark in that this here would be about negative 0.5. So then this would be negative 1.5. You see how I'm subdividing the step from negative 1 to negative 2 into two equal pieces. So that's why that's halfway along. And then we get to negative 2 to negative 3. And we know that these numbers are somewhere in there because the digit in the ones place is negative 2. The tenths place subdivides this step from negative 2 to negative 3 into 10 equal segments. Negative 2.1 would be 1/10 to the left of negative 2, so that's right there. Then we have negative 2.2, negative 2.3, 4, 5, 6, 7, and there we have negative 2.7. We don't have to do anything further on this number line. We see that negative 2.7 is to the left of negative 2.1, and we're asked which number is smaller. So the answer is negative 2.7 is smaller than negative 2.1. To say that in mathematical notation, you're going to be saying that negative 2.7 is less than negative 2.1. Example 5.4 asks, which number is greater, negative 3.42 or negative 3.45? Write the answer in mathematical notation. So now we have numbers in the hundredths place. So when I mentioned before that these steps between whole numbers can be subdivided indefinitely, so far we have subdivided them into tenths. Now we would be subdividing them into hundredths. So what do I mean? This is what I mean. On the number line, between negative 3 and negative 4, there is the number negative 3.4, and there is the number negative 3.5. These two numbers that we're asked to compare, they exist in this space. So what can you do with a number line? You can expand it out. You can just write any subset of a number line as long as you keep that 0 to the right of all the negative numbers and you consider how the negative numbers are ordered as they go down from 0. So I'm going to write negative 3.4 here, negative 3.5 off to the left. So if we cut this space in half, that would be halfway between negative 3.4 and negative 3.5, which would be negative 3.45. This space can be subdivided negative 3.41, negative 3.42, negative 3.43, negative 3.44. It's hard to label when it gets this small, but that means that negative 3.42 is two steps to the left of negative 3.4 when we're looking at these notches of hundredths. So this is negative 3.42, and negative 3.45 is noted on the number line. Negative 3.42 is on the right relative to negative 3.45, so negative 3.42 is larger. Translated into mathematical notation, what that says is negative 3.42 is greater than negative 3.45. Let's move on to talk about ordering small numbers. So small numbers are going to be those between 0 and 1, so 0 point something. When it comes to numbers between 0 and 1, especially those with leading zeros after the decimal, number lines become less and less useful because you have to keep subdividing into ever finer gradations to get to smaller and smaller numbers. So leading zeros is defined in a footnote. Leading zeros are all of the zeros between the left of the number and the first non-zero digit. Typically, these leading zeros are seen in quantities between 0 and 1, so 0 point something. For example, 0.0001 has 3 leading zeros. I realize that there are 4 zeros written to the left of the 1 in that number, but the 0 to the left of the decimal point is not counted because it is not relevant. That number could be written 0.0001, the same as it could be written 0.0001. The extra 0 on the left of the decimal point is often shown just so that you don't miss the fact that there's a decimal point there. Occasionally, computer programs will left pad numbers with zeros to make them a certain length. For example, 647 could be represented as 00647 with 2 leading zeros. Leading zeros are going to be relevant for us because we're looking at decimals right now. So of course you could use number lines, but they just get more and more clunky as the numbers get smaller and smaller. So we're going to go through a couple of examples to look at a few techniques that do a better job in these cases. Example 5.5 asks, which is smaller, 0.25 or 0.050? Write the answer in mathematical notation. When numbers are familiar from currency, like these, you can use that to figure out which one is smaller. What do I mean? Well, what if we took those numbers to be units of US currency? 0.25 would be 0.25 with a dollar sign in front of it, so that is a quarter. 0.050, it's got a 0 hanging off the end, but you know zeros to the right of the last non-zero digit can be left off. So I'm going to write that with the dollar sign 0.05 and note that in US currency that is a nickel. So just as a nickel is less than a quarter, 0.05 is less than 0.25. So here we employed the fact that a nickel is worth less than a quarter. 0.05 is less than 0.25. Now, things don't always come out nicely according to pre-existing currencies and coins. So what's another way to handle it? This is a way that applies to any pair of numbers. And what you do is multiply both numbers by 100 and then compare them. Multiplying them both by 100 preserves the order. It preserves the order of the numbers relative to each other. So implementing this, 0.25 times 100 moves that decimal point 2 places to the right, and you get 25. 0.050, or just 0.05 I could have written, times 100 equals 5. What multiplying them both by 100 does is it puts them on a more understandable scale, or a more intuitive scale. So now we're on this scale and we clearly see that 25 is more than 5. Just as 25 is more than 5, 0.25 is more than 0.05. Of course, we were asked which is smaller, so we would state that 0.05 is less than 0.25. So once again, we're here. And finally, another way is to stack the numbers vertically and compare them digit by digit from left to right. Specifically, stack them vertically lined up at the decimal. Okay, so stack the numbers vertically lined up at the decimal point, then compare digit by digit from left to right. I'm going to stack a 0.050 on top of 0.25. We can ignore the 0 on the left of the decimal point because it's just a placeholder, or it's just cosmetic. But just looking at the tenths place, we see that the top number has a 0 in the tenths place, whereas the bottom number has a 2 in the tenths place. 0 is less than 2. So on the basis simply of the tenths place, we see that 0.050 is the smaller number. And that's the third way we can arrive at the fact that 0.05 is less than 0.25. Turning to example 5.6, we see that actually this value on the right-hand side is, if you put a dollar sign in front of it, that's a penny. And you may realize, looking at this number on the left, that this is going to be something that is not really represented in our currency. And we'll see the implications of that in a second. So let's just do the two ways, the another way and another way from example 5.5. So we'll call this the first way. So in example 5.6, we are asked, which is smaller, 0.0076 or 0.01? And then to write the answer in mathematical notation. So the first way is to multiply both numbers by 100 to put them on a more intuitive scale. 0.0076 times 100 is 0.76. 0.01 times 100, move that decimal 2 to the right, and you get 1. Just as 0.76 is less than 1, if we were thinking of that in currency, that would be 76 cents versus $1. 0.0076 is less than 0.01. So the answer in this case is that 0.0076 is less than 0.01. Using the second way, let's stack these numbers vertically, lined up at the decimal point. So 0.0076, I'll put on top. You can put either number on top. It doesn't matter. Just keep track of which one is bigger and which one is smaller, and which one you're talking about when you assign that. Lined up at the decimal, we get 0.01. So looking at the tenths place, which is the first place to the right of the decimal point, they're equal. These two numbers are equal in that digit. They're both 0. Moving to the hundredths place, the second place after the decimal, we see that 0.01 has a 1 in that place, whereas 0.0076 has a 0 in that place. So based on that hundredths place, you can see that the number on the bottom is larger. Because 1 is greater than 0, and that's the first digit from left to right where they actually differ, 0.01 is greater than 0.0076. Given that this question asked which was smaller, I'm going to write that 0.0076 is less than 0.01. Which technique should you use? Whichever makes the most sense to you, either or both, all and every.